Oh, we're going. I'm really close to the camera. All right, so we're gonna do this here. I'm hoping that I will get my Surface stylus soon, and so we won't have to do the janky whiteboard. The problem with it, it's very reflecty. So if I put too much light, there's too much glare, and if I don't use that much light, then you get me lit like this, which is weird. None of you care. Here we go. We're going to do, off of the Chapter 12 test review, we're going to do, well, all the problems, but this is the 3 balls problem. So, here is our drawing. I suppose I could have put the drawing up first. Okay, so we've got... All right, and so here's our axis. Remember, every one of these problems, your axis is important, right? Okay, so we've got these 3 particles. The first one has a mass of 5m, second one has a mass of 2m, one at the end has a mass of m, and then all of these distances are L. So the distance from here to here is L, and the distance from here to here is 2L. Okay, so question A asks us to find the rotational inertia, right? So in this, remember, inertia is the kind of rotational counterpart to mass, right? So in the same way that you can add mass, you can add inertias, all right? So all I'm going to do is I'm just going to find the rotational inertia of these 3 particles. So my total rotational inertia is the rotational inertia of the 5m1 plus the rotational inertia of the 2m1 plus the rotational inertia of the m. Now remember, this is kind of what this problem is about. So the rotational inertia of a particle is just mr squared. Okay? So, sorry, I was looking to see if the green showed up on the camera here. All right, so let's see. So for the 5m one, it's mr squared. So the mass is 5m, the radius is 0. Don't forget to square it. Okay? So this one here actually doesn't have any inertia because it's a point particle rotating, but since a point doesn't have any sort of radius on its own, you can't rotate something that doesn't sort of have size, right? Okay? All right, our second one has a mass of 2m, and the radius is L. Don't forget to square it. And then the last one has a mass of m, but a radius of 2L. Don't forget to square it. All right? So we get 0 plus 2m times L squared plus m times 2L squared. Remember, it's quantity 2L. So this is 2L squared becomes 4L squared. So we get 4mL squared. Add our like terms, and you get 6mL squared. Okay? So that's part A. That's how you calculate the rotational inertia for that thing. All right? Now, part B gives us the numbers, and it asks us to find the starting rotational inertia. The starting angular acceleration of it. Okay. So let's make a note over here. We just found our rotational inertia for the system, and it's 6mL squared. All right. So now what we need to do is to find the angular acceleration. That angular acceleration is going to be dependent on the torque. All right. So I'm just going to write a net torque equals net torque equation. So on one side of the equation, we've got I times alpha. We know our I, and we need to solve for alpha. Okay? On the other side of the equation, we've got our torques. Now, there are 2 ways you can do this. Option 1 is find the center of mass of the system. Okay? I don't know where it is because I didn't do it this way. My guess is that it's going to be kind of over here somewhere, right? And then you can treat the whole thing as having a mass of 8m, right? Because that's the mass of the whole thing. And then just do force of gravity, so 8mg times whatever that lever arm is for your center of mass. All right? But I tend to get a little bit nervous when I use center of mass for stuff like this. It does work in this instance. There are some other instances, though, where it doesn't work. So what I'm going to do instead is I'm going to calculate the torque generated by the 5m thing, the torque generated by the 2m thing, and the torque generated by the 1m thing. Okay, and just add them all up. Okay, So our I is 6ml squared times alpha equals the torque from the 5m thing. Well, that's the force is 5mg times our lever arm. Well, remember our pivot point is here at the end, so our lever arm is 0 again. So once again, that 5m guy does not matter. All right, and then the torque from the 2m thing is the force of gravity from it. So 2mg, there's the force, times our lever arm is L, plus the torque from this last guy. So all we're doing here, you guys, is we're just doing force of gravity. I probably should have drawn in my force of gravity vectors, but so there's the force of gravity on this guy, and there's the force of gravity on this guy, which is what I'm doing now. So that force of gravity is mg, and then our lever arm is 2L. So this guy goes away. We've got 2mgl plus another 2mgl, that's 4mgl. So I'm looking at 6ml squared alpha equals 4 mgl. And then let's see what cancels. So the m's cancel, right? We're trying to find alpha. So let's see, I can divide both sides by L. And so it looks like alpha is going to end up being, I got to divide both sides by 6L. So I get 4g over 6L, which obviously is 2/3 GL. All right. And then the problem tells you what G and L are. So at that point, you can just plug in, tells you what M and L are. Notice the M doesn't matter here, right? Because all of our forces and torques are proportional to the masses. Okay. So there we go. So there's our acceleration. Cool.